So let me remind you where we were. So we're talking about matroids, and remember that originally I defined a matroid to be a set and a collection of independent sets satisfying these three axioms. And then we talked about bases, and we're in the middle of proving a theorem that says that a collection B of subsets of E is the collection of bases of a matroid if and only if these two axioms are satisfied. We're in the middle of proving this. We're going to complete the proof today. But just to make sure that you understand this circle of ideas, the idea is that if you start with a matroid defined in terms of independent sets, then you can define a collection B consisting of the maximal independent sets. Maximal sets in I. And remember that maximal means maximal by containment. Okay? The point is, if you do this, then you're going to get a matroid with the basis definition. So E is a set, B is a collection of subsets that satisfies these axioms. But this goes the other way around. If instead I give you a matroid in terms of the basis, then you can tell me what the independent sets are. So you're going to tell me that the independent sets are the subsets of the basis. Subsets of sets in B. And it's a fact which, again, we're in the middle of proving this, but it's a fact that if you start with a matroid defined in terms of bases, and you define this collection I, then this collection is going to satisfy these axioms, and so it's going to give you a matroid. You can go around this circle as many times as you want. If you start with this one, with the matroid in terms of I, then you define B, you get a matroid in terms of B, but this is the same matroid. So that now if you take this collection B, and you define the subsets I of the sets in B, and you're going to get back the same matrix. So we're basically going around a circle and not doing anything at all. We're just giving different definitions of the same object. Okay? And we were almost done proving this equivalence. We were in the middle of proving that if you start with a matroid, if you start with a collection of sets that satisfying B1 and B2, B satisfying B1 and B2, then you got a matrix by saying I equal subsets of sets in B and we were in the middle of proving that if the collection script B satisfied axioms B1 and B2, then the collection I satisfied the axioms I1, I2, I3. Satisfies I1, I2, I3. This is what we're in the middle of proving. And remember, we had already proved I1, we had already proved I2, and we were in the middle of proving I3. So to prove I3, we were proving basically that statement. And we were doing, so we were taking induction on R minus J. That's what we were doing. We were going to prove that statement that if I is less than J, I mean if the size of I is less than the size of J, then we could augment I with a set in J, with an element of J. And remember we had done the first step, which was the what I call this step 2a, which is that we did this for r minus j equals 0. Okay? And we were in the middle of step 2b. We hadn't started step 2b, which was the inductive step. It said, if I prove it, for r minus j equals k plus 1, no, equals k minus 1, then it's true for r minus j equals k. So that's where we were.
Yeah. R is the cardinality of
And R was the cardinality of all the sets in B, which we showed were equicardinal.
Oh, okay.
So R equals the size of all the sets, size of any set in B. Remember, we proved that all the sets in B had the same size. Okay, so let's do that. So take I and j in this collection script I with I less than j and with r minus j equals k. We want to prove that we have the exchange axiom here. Okay? Now, what can we do? Well, all we know is that the collection script B satisfies axioms B1 and B2. So we somehow need to go from basis exchange to independence exchange. Okay. Here we have independence exchange, we're going to have to use basis exchange. And so really, the natural thing to do is say, well, if I want to exchange from I to j, let me find some bases related to those. When again, basis just means elements of script B. And so what I'm going to do is consider a B and A containing I and a B containing j, which
A and B are bases?
are in this collection script.
Well, we don't know that script B is a basis yet.
We're just calling it.
Okay.
We only know that script B
Okay.
satisfies properties B1 and B2.
Okay.
And of course, we're headed to the idea that because script B satisfies the basis exchange axiom, then we want to do an exchange from I to j. Maybe we can do it from A to B in a way. Okay. Okay. So let me okay. So let's look at this. We have that I is less than B, right? Because B contains J. And so
No.
what I want to do is use this step right here. Okay. That I know that if my set J has size R, then I can actually do this exchange. So from my base case 2A, I know that I can find B in B minus I with I union B in script I. So here I'm just using the base case of the induction. Okay. Does that make sense? And so what one might hope is that I want to add an element of J to I. I managed to add an element of B to I. Well, if we're lucky enough that this guy is in J, then we're done. Okay. So first case is that B is in J. Then what happened? We found I union B in my collection I for B, which is in J, and is not an I. And this is exactly the B that we were looking for. So in that case, we're done. The second case is that B is not in J. Okay? But now look at this. I know that I union B is in my collection I. Okay? Now, I'm going to claim that J union B is also in I. Why? Well, because J union B is a subset of B. J is in B, and little b is in B. So J union B is a subset of a set in B, therefore it's in I. But what happens? Now I have these two guys. I have that the size of I union B is smaller than the size of J union B. And my plan is to apply the induction hypothesis. Well, if you look at R minus J union B,
It's K minus 1.
well, R minus J was K, and I subtracted another element, K minus 1. Okay. So because I have this situation, I can use the induction hypothesis and find, let's call it an element C in this guy that I can add to this guy. An element C in J union B, which I can add to I union B. Okay. Well, if I union B union C is in my collection I, then I union C is also in my collection I. Right?
We know B does not equal C.
We know B does not equal C. Why do we know that?
I don't know. We should probably think about how big it is.
Actually, so
Well,
I was a little bit careless, and I should have said something more here,
Oh, well,
which is that
B is
from
in
here to
both.
here you can
Yeah.
find
Yeah.
C in this guy minus this guy.
So it can't be
There
B.
you go.
Yeah.
So it can be B.
Yeah.
So it really has to be. I mean, J union B minus I union B is just J minus I. So I found C in J minus I such that I union C is in I. And that's proof. So that was the induction step. Okay. And remember, I promised you guys that actually in this induction, the induction step was easier than the initial case. This is not what usually happens, but in this case, it took us more work to do the base case of the induction than to do the inductive step. But we did it, and so this is it, and we're done proving our theorem. And therefore, what we have proved is the equivalence of these two definitions. So you can either define matrices in terms of independence, or you can define matrices in terms of bases, and you're really talking about the same objects. These are equivalent definitions. Any questions about this proof? So let me ask you guys a question. Was this proof harder or easier than you expected it to be when I started?
I think that base case of the second part was a little bit harder than I thought it would be.
Yeah, did someone expect this to be easier than it was? Expect this to be harder than it was? I mean, Vladimir said last time, this is a lot of work for I mean, it took us a lot of work to prove some simple statements, and I do agree that. I mean, I do agree that it was tricky. That let me actually organize what I want to say, because I want to make a point here which is slightly philosophical, but important. Doesn't mean that what I'm going to say is not mathematics. Slightly philosophical point. We have two definitions. Two axiom systems. One for independence, and one for bases. And at least I think you'll agree that it was real work to prove that these two were the same thing. So it was proving that these two axiom systems are equivalent is real work. So it's really not easy. But, and this is the point that I want to make, and this is where I really want you guys to think maybe a little bit differently from how you are used to thinking when you sit in a class. I mean, I can tell you, okay, this is the definition, and then I can prove some theorems about it. Okay? But I really want to ask. I want you guys to ask yourselves, you know, why this definition? Why not another one? I mean, imagine what happened if I asked you to come up with the definition of the axioms of a basis. The point that I want to make is that this is really the difficulty here. The difficult thing is to actually invent these two definitions. The real difficulty is coming up with the right definitions. Coming up with good axiom systems. And this is the point that I want to debate for a while. I want you to think about this and evaluate and be critical about this and say, okay, you know, I see some definitions. Am I convinced that these are good definitions or not? So this is really the next question I want to ask is, are these good definitions? Or otherwise, why are we going to bother and take a class on this definition if we don't think it's a good definition?
Well, we aren't really in a position to have an opinion on that, because my understanding is the reason that we're defining matroids is because they tie together ideas in graph theory, linear algebra, and other areas. And so until we know what those things they're tying together are, we can't have a judgment on whether these are cool or not.
Yeah, and that's a very good point. The point is, how do you judge? How do you judge if these are good definitions or not? And that's exactly the point that I'm trying to make here, which is, what if you're inventing a theory and you think, well, maybe this is a good definition. Is it worth it to continue, or am I just playing with this useless definition? Okay, and this is really the question I want to ask here is this a good definition? Question. For example, this initial axiom system. Is it good? What does that mean? Well, you know, precisely that's why I said that it's a slightly philosophical question, because because there's no yes or no answer to this. Okay. Well, what are some arguments in favor or against? You know, why do you think this is a good axiom system, or why do you think that maybe it's not?
You mean separate from the idea of a matroid or of whatever? Like, is this this particular way of defining it is what you're asking about?
No, I'm asking, is this object that I defined for you worth studying?
Okay.
Do you want to spend a semester studying an object that satisfies properties I1, I2, and I3? Or are you wasting your time here? I hope you're thinking about this if you're going to spend a semester working on it. I think so far we have reasonable evidence that this is interesting, and this is I mean, some reason to think that this is some reasons to think so. The first reason is that you did already see that this definition applies to three different kinds of problems. Simultaneously applies to linear algebra. It applies to graph theory. It applies to matching theory. We saw that it also applies to these Dick paths. Some people care about Dick paths. And we'll see that there's others. We'll see that there's other examples that this theory applies to. Okay.
Can I say another reason?
Yeah?
So, simplicial complicities are very well studied and very important for a lot of reasons. So this is kind of a special set of already well-studied objects.
So these guys are simplicial complexes. And if you've done even a little bit of topology, I think you're probably convinced by now that simplicial complexes are important things. Well, these are simplicial complexes. And actually, we can say more. Because remember, we know that these are exactly the simplicial complexes where the greedy algorithm applies. We proved this. These are exactly the simplicial complexes where the greedy algorithm applies. And I think you will agree that the greedy algorithm is a natural strategy for solving problems in real life. And so if you care to know when this is going to work, then that means presumably you care about matroids. These are two positive arguments. And does anybody have some arguments why they don't like these definitions?
I don't know, I guess from experience from linear algebra, it's also good to work with dependent sets.
So maybe some drawbacks. What about dependent sets? We keep talking about independence. What about dependence?
It's essentially isomorphic, though, right?
Yeah, talk about independence.
I mean, this is meant to be some characterization of independence, but I agree. In linear algebra, it's very often the case that you care about dependence, and you want to say, okay, let me write down a linear dependence. I'll write down an equation that says, okay, this guy and this guy and this guy are dependent. Whereas here, the focus seems to be on independence. Keep thinking about this. The whole semester, this is really an ongoing thing to think about. Is why do you think this is good? Why do you think this is not good? Personally, if you tell me this, I'm happy. If you tell me that this theory applies to all these different things and it's equivalent to the greedy algorithm, I might think, okay, that's cool. I like that. But maybe you're not convinced, and so be, you know, if you're not convinced, then look for further evidence or okay. Now, another point that I want to make is, and it's more related to what I was trying to say here, is what about this? These axioms for bases. And what I mean is this. Imagine that you decided, okay, I care about independence. I care about this definition of independent sets. And now I'm trying to come up with a definition with an axiom system for bases. Well, I'll tell you two good things about this system. You know, one good thing about B1 and B2 is that they're easy enough that you can prove them. You want axioms of your bases that you can actually prove. So these guys are, the axiom system is easy enough. That you can prove these things in a matrix. So if you know that I1 up to I3 hold, then you're going to know that B1 and B2 hold. And normally, the word mathematicians like to use for this kind of thing is weak enough. These axioms are weak enough that, you know, we saw a proof that if this holds, then this holds. Okay? But there's also the other advantage, that they're strong enough that you can go the other way. They're strong enough that if I start with them as the basic things, then you can recover the whole theory. Okay. And you might not be too impressed to this point, but if you start thinking about things like this in the future, you're going to see that this is really a hard balance to strike. It's a hard balance to strike to come up with a definition that, you know, you can prove that it's true, but your definition, so it's easy enough that you can prove it, but it's hard enough that you can do things with it.
So does that make the B's weak enough, or does that make the I's weak enough, or they're both kind of weak enough?
So what we just proved is that they're exactly equally weak or equally strong.
Yeah.
Right? So, I mean, you could exactly have said this in the other way. If the B's are the fundamental thing, then the I's should be weak enough that you can prove them, and strong enough that you can recover the B's. This is a balance that is hard to strike, and we managed it. We showed that I and B, that these two axiom systems are equivalent.
Can I say another potentially good thing about both? I think both of these axiom systems seem to be somewhat constructive or whatever. It's like they're not so abstract that you look at them and you don't know what to do. Like they give you a way to work with the objects that you're defining in a pretty clear and concise manner. Like you could probably come up with an axiom system that's equivalent, that's so abstract that people will look at it and have no idea what you're talking about. You wouldn't want that.
Right, that's a very good point. They're very concrete axioms, so that, you know, if you want to prove maybe a theorem in graph theory, then where do you start? You know, you have a graph, so it's a vertices, edges, paths. There's all these kinds of different concepts. If you decide that maybe this is actually a matroid theorem after all, then this really streamlines your argument, and it says, well, these are the three things that you know about. So it might make it easier to think about these things. Okay. Now the reason that I wanted to kind of start this discussion is that now we're going to Vladimir absolutely read my mind, because I want to talk about dependence now. But I really want you guys to keep this in mind when we talk about dependence. think I'm gonna need this. I can erase this. And let me ask the question, what about dependent sets? Okay. Maybe these are the things you care about, so let's study those. Okay. And again, maybe a good way to motivate this discussion is just to go back to the same example that we keep talking about. So either if you have a vector configuration like this, where this is the vector A, B, C, D, E, F, or the graph. The graph will be blue. A, B, C, D, E, F. And we said, okay, this is a matroid, and we saw it's the same matroid, and we saw several descriptions for it. So one description is we said, okay, the ground set is definitely A, B, A, B, C, D, E, F. And we said, okay, the independent sets, this is the way we first defined this. We made a list of independent sets. Empty set, A, B, C, D, E, A, B. And the marker is going to run out of ink before I finish. It's really a long list. And then we said, okay, well, this is maybe not the best way to do this. A more economical way is to say, what are the bases? So, okay, they're ABC, ABD, ABE, ACB, and ACE. And we said, okay, this is somehow a more economical way of saying this. More economical way. Description. Well, I can do exactly the same thing with dependent sets. So I might just say, okay, let's make a list of the dependent sets. Dependent sets. And let's call them script D. Okay. So what is dependent? Well, any set that is not independent. For example, F does not appear on this list. DE does not appear on this list. AF does not appear on this list. BF does not appear on this list, and then you start realizing, okay, CF, blah, blah, blah. And then again, you're going to realize that your list is very long. For example, A, B, C, E, F, you have to make a very long list. Too long. And so, what's a more economical description? Well, if F is dependent, then everything containing it is dependent. DE is dependent, and everything containing DE is dependent. So it's pointless to make that long list if you can just make a shorter list. And your shorter list says, okay, F is dependent, DE is dependent. What else should I put on this list?
Maybe like ADC. Does that need to be? No, no.
ABC?
ADC.
ADC.
No, BCD, I mean. BCD.
So those are independent, right?
Yeah, those are independent.
ABC is independent, ADC is independent.
Yeah.
What is dependent that I haven't listed? Or am I done?
BCD, BCD,
And all the same thing, yeah.
and all those ones on that plane.
Free off that.
Yeah.
For example,
Yeah.
B plus C is E.
Yeah.
So BCE is dependent, and that doesn't follow from these guys.
Yeah.
So BCE should be on my list.
And BCD.
And for the same reason, BCD should be on the list because D is the average of B and C. So B plus C minus 2D is 0. So BCD is on my list. Anything else? Well, you can stare at this picture long enough to see that you're done. Or another thing you can do is look at this picture. So what's F? This loop. What's DE? This circuit. What is BCE? It's BCE. What is BCD? Is BCD. And then here it's a little bit clearer that we're done, because these are all the circuits. These are all the cycles. Okay. So this is a more economical description. And we're going to give these guys a name. Okay. And the name is circuits. And the reason they're called circuits is precisely because that's motivated by the graph situation where you look at them and they look like circuits. So these are the circuits. Okay. Now, question is this enough to determine the whole matroid if I give you this list?
And the ground set?
If I give you this list and the ground set, can you tell me what the matroid is?
Probably. Just
We wouldn't know what A.
Yeah.
We wouldn't know where to put A.
yeah, definitely. Well, that's definitely
The
Or you
subsets of E that are not named in anything.
Okay, so first let me say what a circuit is, okay? Because I haven't really made the formal definition. A circuit of a matroid is simply a dependent set that is minimal. Okay, this is my list of dependent sets, too long, and I just kept the minimal ones. Minimal dependent set.
so minimal again with respect to inclusion,
Subset of
not with respect to carbon.
And minimal-
clearly.
You'll see that this is going to happen the whole course, and I'm going to forget to say it, but this is the convention is always, when you
Yeah.
say minimum, that means smallest in number. When you say minimal,
Yeah.
that means smallest.
Well, in the basis
With
situation, they were all the same size, so it kind of made sense.
Uh-huh.
Here, like, we have different cardinalities.
That's a good point.
Yeah.
When I listed the independent sets, and I said, okay, the important ones are these ones, the bases. These happen to have the same size. Okay? But if you list the dependent sets and you now care about the minimal ones, these do not have to be the same size. And so here you're more easily confused about minimum or minimal. So be careful about that. Okay? And also this is going to show you that these guys are truly different from bases. You might think that independence and dependence are the same thing. Well, these two objects certainly have different properties.
So minimal is just saying that no other dependent subset that's smaller in size.
Exactly.
Or
No,
there's
no,
other-
not in size. Minimal dependent subset of E means that it's dependent. So let me say it this way. So C is a circuit if C is dependent and no subset of it is dependent. That's what it means. Okay. And so let me first think what I want to do in the Oh, I have time. So first let's talk about why the circuits determine the matroid. So in fact, we can say it opposition. The circuits determine the matroid. The circuits and the ground sets. So E and C determine the matrix. And I saw several of you nodding your head and telling me that you see why this is. Because C is the collection of circuits. Now, what I heard some of you say is that that allows me to define dependence. Okay. These are the minimal dependent sets. So the dependent sets are these and the ones containing them. Dependent sets are D equals sets containing a circuit.
Supersets.
Subsets of E containing a circuit, or supersets of a circuit. E containing a circuit. And if you define dependent sets, then the independent sets are the other ones. Independent sets are just all the sets that are not dependent. So the circuits determine the matroid. Okay? And now, in light of this kind of philosophical discussion that I had here and here, what I want us to do now is try to figure out what the circuit axioms would be. So I want to write a theorem that says a collection of sets is the collection of circuits of a matroid if and only if C1, C2, C3, C4, whatever I need. Okay. So what I want us to do is to decide which are the key properties or the axioms that we want to keep track of for C. And now that we have two axiom systems, that will serve us as motivation to figure out what to write here. And this is where I want you to think a little bit differently, because I don't want you to read the book and say, okay, these are the axioms. I want you to think about why the book picked the right axioms and you agree that these are good axioms. So the first thing you might decide is, okay, what was the first axiom of this definition? Is that the empty set is independent. In other words, this is kind of a non-triviality thing that says, okay, at least the empty set is independent. There are some independent sets there. What was the first definition for bases? So
it wasn't
wish I had-
empty.
We once said that there was at least one basis. So again, it's a non-triviality condition that says there's something to this matrix. So what would you say that the non-triviality condition is for circuits? The empty set better not be a circuit. Because if the empty set is a circuit, then everything is going to be dependent and you don't have a matrix. So the empty set is not a circuit. It's a good thing. Empty set is not a circuit. Second axiom. Let's go back to the second axiom for independence. It said if you start with something independent and you take a subset of that, then that's still independent. So this is something about going from something to a subset of it. So what would you say it is in this case?
Anything containing a
circuit is dependence?
But we're talking about circuits, so I don't know what the word dependent means.
Anything containing circuits.
But I mean, yes,
Anything
yes, but I want you to rephrase that so that you don't use the word dependent.
Well, so we want it to be, if you remove anything, you get an independent set.
What is independent?
So a subset,
In the B,
subset of
a
circuit,
basis.
not a circuit.
That's exactly right.
Yeah.
So that you're saying the same thing, but you never use the word dependent or independent.
Yeah.
So a subset of a circuit is not a circuit. I want to be a little bit careful. So a proper subset, right?
Yeah.
Otherwise, it's not a very interesting definition. A proper subset of a circuit is not a circuit. Because the idea is that the circuits are the minimal dependencies. So anything that is included in them cannot be a dependence. So a proper subset of a circuit is not a circuit. Good.
I mean, that's how you defined it.
It's right. This is true basically by definition. What about axiom B2? What happened to axiom B2? I want to show you guys something here, which is that the axiom that I called B2, I would almost want to call it B3. If A and B are bases, blah, 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 blah. It tells me how to build another basis. What would axiom B2 be if this is I2 and this is C2? This could be an axiom that says something like a subset of a basis is not a basis.
Or a superset. Is
Or a
not
superset of a
dependent.
basis is not a basis. Why is that axiom not here? Because it's implied by this one.
Yeah.
And so probably when people were inventing this definition, presumably they had an axiom here that said B2, a subset of a basis is not a basis. But then they realized, oh, I don't need that.
Yeah.
And that's why this guy is missing. And this guy is called B2, but I think you'll agree that B2 sounds like I3. It's some
Yeah.
kind of exchange axiom that says, if I start with two guys, I and J, I build a third one, I union J. If I start with A and B, I build a new one, A minus A union B. And so for circuits, I want something like this that says, if I have two circuits, how do I build another? So if C and D are circuits, how can I build another one? We saw how to do it for independent sets. We saw how to do it for bases. And now we need a little bit of a flash of inspiration to think of how can you make circuits from circuits. And the inspiration, usually in these cases, comes from the motivating examples, you know? Because we know that graphs are matroids. We know that vector configurations are matroids. And so we can say, okay, in a graph, how do you make a circuit from two circuits? If I have two circuits like this, C and D, how do I make another circuit?
Connect them.
I can't. I don't see any other circuit there. But if they happen to look like this,
Oh, I see.
how do I make another circuit? I go around. In other words, if two circuits have something in common, I can get rid of that and get another circuit. If C and D are circuits and they have something in common,
Yeah.
then I don't need that C. I can find a third circuit that doesn't use it. And I can find a circuit which basically uses C and D and doesn't use X.
Which uses a circuit.
So
Wait, so can we talk about that? Oh yeah, I see. So on that BCE and BCD, you can remove the BC from both and you have the... Yeah.
exactly. So in this example, if you look at the circuits, Just wait for the camera to arrive here. Any day now. If you look at these two circuits, DE and BCE, they have something in common. E. What that's telling me is I can find another circuit if I don't use E. And I use these guys, B, C, D. Well, here it is. This is another property. This is a property of circuits. Is it a good property? Is it enough? Well, now we're faced with this question. Is this a good axiom system? It's good if we can prove that it's equivalent to what we have so far.
And do we need C2?
And do we need C2 or does it follow from C3? And the good news is that this is a good axiom system and we're going to prove it. Okay?
And we do need C2?
And we do need C2. So, and this is what we'll do next time. Okay? We'll show that this is the right axiom. All right. I'll stay for questions, but I don't want to stay late. So you guys can go if you want, and I'll take questions.
So I'll just run up right after my class at 3 and meet you in your office?
Sure.